Hello students, welcome back. Let's see, in section 3, we talked about the general solution theorem. We proved the first half, linearly independent solutions exist, but we did not prove the second half. The general solution can be written as a linear combination of those y1 through yn. Let's postpone this second half, because it's really deep. But let's take it for granted, and then let's go to example problems. Exam problems in section 4 of this notebook. Cauchy-Euler equation. In this structure, second power times second derivative, first power times first derivative, zero power times no derivative, and in general, nth power of t times nth derivative, and so on. That's Cauchy-Euler equation. How to solve it? We discussed the substitution method, so let's review that. We just make an educated guess, t to the s power, and then derivative, second derivative. For higher order, you can take derivative k times like this, and then put those into the original ODE. So y double prime is equal to this, y prime is equal to that, y is equal to t to the s power, yes. You've done this before. And then please note that t squared and minus 2 power, t first power minus 1 power, they just cancel each other out, and we have t to the s power common. So right hand side is 0, so either t to the s power is 0, or this expression is equal to 0. When t to the s power is equal to 0, that means y is equal to 0, so we have a solution. A singular solution, but it's a solution nonetheless. But then again, if you just find singular solution, then you're gonna get something like, 10 out of 100, or something like that, 1 out of 10. The majority is this part. So let's solve this characteristic equation. It's a quadratic equation. And then what do you get in the end? Oh no, this is for general case. Quadratic case, yes. 2 different real root. And then double root, we have log of t popping up. And then we have complex roots. Then cosine of log, sine of log. You're gonna get this kind of expression. Oops. There's a typo here, excuse me. I forgot putting something in there. Okay, coefficient. All right, and then let's keep those. And then let's go to example problem, and let's go over these very, very quickly. Substitution method. Let's see. T to the s power, and I take derivative, and put those into the original ODE, as you did see in the second part. And do your computation, and t to the s power is common, so factor it out. What's left is a quadratic polynomial. Solve that quadratic equation, then you're gonna get characteristic values, 1/2 power, 3rd power. Oh, we have a typo here. Excuse me, another typo. We don't have t power there. T to the 3rd power. Oops. Okay, all right. Sorry about that. And then you can check your solution like this using mathematical command. Okay, all right. How about this problem? This problem, you're gonna get a double root. T to the s power, and plug those in. You have this middle part. And then, as usual, t to the s power is factored out. What's left is a quadratic equation. So then you end up with a double root. So we have s value is 1/3. So we have t to the 1/3 power that's coming. But another one that pops up is that times log of t. Yeah, this case. And we'll answer y log t a little bit later. How about the last problem? Plug in t to the s power, and then factor t up to the s power out. What's left is a quadratic equation, and then it has a pair of complex roots, 2 plus 3i, 2 minus 3i. So the real part, t squared, and then the imaginary part, 3 log of t, 3 log of t with sines and cosine. By the way, why do we have all these? Well, it's actually because of this, t to the a plus b I power is equal to, let's see, whenever you have general power, general base, you can rewrite it as a standard exponential like this. Whatever power that was there before, a plus b I times log of t like this. In general, if you have a to the b power, it's exponential of b log of a. I'm using this formula here. And then what about this a plus bi thingy? That's sine and cosine. And then we have this log of t coming. So why this thing is becoming sine cosine of log? Okay, I'll stop here and I'll ask you to complete. You can use that the exponential formula for sine and cosine that we discussed in lesson 1a. I don't want to go too deeply in that. It's left to the students. In any case, that's how you can handle in substitution method. But then again, why in the world we have this log and the sine cosine log? Those are a little bit unclear at this moment. So let's go ahead and do this change of variable method, which is difficult to apply, but theoretically a bit more sound. Our textbook author does it only this way, which I don't really like, because if you actually try this method, you'll see it's harder, but theoretically sounder. Okay, let's begin. Whenever you have Cauchy-Euler equation, we take a substitution, t as e to the x, consequently x is log of t, and then express y as a function of x. So instead of y of t, rewrite it as z of x. Okay? Alright. And then take derivatives. Okay, y of t is equal to z of x, where t and x are related like this. So if you take the derivative, y prime of t, alright, and the right hand side, what do you get? And we take the derivative by x, so we get z prime of x, and then dx over dt, that pops out by chain rule. What is dx over dt? X is log of t, so that derivative is 1 over t. So the conclusion, t times y prime is z prime. So this part, that's going to be z prime. Let's take one more derivative. Okay, here y prime is z prime times 1 over t. Take the second derivative. By product rule, z double prime times, let's see, by chain rule, you have to take the derivative of the inside, dx over dt, which is actually 1 over t because x is log of t, and this is there before, and z prime of x, which was there before, times the derivative of the second function there. Simplify, well, this is 1 over t. 1 over t was there before, so these two generate 1 over t squared. This one, another 1 over t squared, except for negative sign. So taking the t squared out, what do you get? T squared times y double prime is z double prime minus z prime. So you can substitute like this. Now, once you do that, this goes in place of t squared y double prime, and this one go to this, sort of a z prime, and then y is equal to z, y is equal to z, so y just changed to z. So function didn't change, variable changed. Change of variable, t and x are related, but y and z, they are the same. So after that, what do you have? We have a second order linear equation with constant coefficients. And we know how to do this. Now these are higher order cases, excuse me. We're going to consider higher order cases in section 5. So constant coefficients. So basically what we can do is you can use Laplace transform method or whatever. You know, it's constant coefficient, you should be able to handle it. Let's go back to the example problem and let's try to apply that. This one is not going to be too interesting. So let's go to this change of variable method. Okay, from here, let's take the change of variable. T is e to the x power, x is log of t, and then z and y are the same. And then we take the derivative. Y prime is equal to z prime, and by chain rule, however, we have dx over dt, which is 1 over t. You see, x is log of t, so dx over dt is 1 over t. So what do we have? Flipping this denominator to the other side, t times y prime is z prime. So this is going to be z prime. And then y is going to be z. Okay, now from here, y prime is equal to z prime times 1 over t. Now take the second derivative. Product rule, so derivative of the first function, and don't forget this derivative of the inside, the chain rule. And that first function times the derivative of second function. Either way, you're going to get 1 over t squared. So you see 1 over t squared factored out. We have z double prime minus z prime. So we get this. And then that goes in place of that. And then if you simplify that, this blue and then green, what's left is a second order equation of z with constant coefficients. And we'll get this. We have double root. So z can be written as exponential 1/3 power of x and x times exponential 1/3 power of x. Look at this part. Let me highlight it in different color. Let's take brown. Black part is straightforward. Let's look at this brown part. And black part, let's see, you can use this, what do you call the exponent rule. You can use e to the x to the 1/3 power. But this brown part, well, you can do the same thing, but the x over there is special. Now e to the x is t. So e to the x 1/3 power, t to the 1/3 power. So we have t to the 1/3 power. And then we have t to the third power, same way, e to the x is t. And what about this x? X is log of t, and that's how log is popping up. So yeah, we do get log of t. So if you use the change of variable method, the advantage is you can understand how in the world this log is popping out. That's the advantage. Disadvantage, the computation here is a heck of a lot harder compared with substitution method. Substitution method, all you have to do is take the first step, right? T to the s power. And then do your computation. It's easy computation. And then once you get double root, just remember t to that power and then log of t popping off. And that is sufficient. As for those little holes here and there, they're all taken care of by this theorem 3.2, the general solution theorem. So no problem there. Well, through this change of variable method, we learned how in the world log of t is coming out. That's sufficient for us. So in the end, I believe most students will be using the substitution method. It's easier, so that's what I expect. And log of t, we went through the justification here, so I hope everybody remembers. How about the last problem here? Okay, we have sufficient time, so okay, all right. Let's show this change of variable method again. T is e to the x is log of t, and z and y are the same. And simply taking the derivative, we have chain rule dx dt, which is 1/2. And as before, you get ty prime is equal to z prime. Same computation. These two is same computation, so a lot of students will just skip and get this and that directly if you use change of variable method, which I believe most students won't. Anyway, plug in those and then you get an equation of z with constant coefficient and solve everything. In the end, we have this complex root. Characteristic value is 2 plus 3i and 2 minus 3i. So you can express those as exponentials like this, or you can do sine cosine like this. All right, what is x? X is log of t. That's why log of t is popping off inside sine cosine. See? X is equal to log of t. How about exponential? We saw those before. We saw this before. E to the 2x can be written as e to the x to the second power. So this is t to the second power. So exponential part, it'll become the power part. And then sine cosine part, you're going to get coefficient times log. You can check those from the change of variable method. Now let's go back to substitution method. Computation is a lot easier. Once you get your final expression, then just rely upon the formula. Real part becomes the power of t, and imaginary part, log of t, goes inside sine cosine. No problem there, because we proved everything already. Okay, alright, I admit it, I didn't prove the latter half of this general solutions theorem, but once I did it, then all the whole will be completed. So yeah, that's fine. Now section 4 is complete. Section 5 is going to be some higher order Cauchy-Euler equation, and I'll leave most of those problems as exercise problems for each student. We're going to concentrate upon completing section 3, the proof of that general solutions theorem.